Module 9, Chapter 20. Now, let's talk a little bit about the hormonal control of blood pressure and blood flow. Hormonal control is going to help provide short-term and long-term regulation. The first hormone I want to mention is called antidiuretic hormone, which is abbreviated ADH. ADH is produced by the hypothalamus, but it's stored and released from the posterior lobe of your pituitary gland. Now, it's going to be released in response to various triggers in the body, such as a decrease in blood volume, an increase in the osmotic concentration of your plasma. So that means your plasma starts to have more dissolved solutes within it. Or it can be released in response to another hormone called angiotensin II. Now, antidiuretic hormone has two effects that are going to have an effect on your blood pressure. One, it produces peripheral vasoconstriction. So remember, decreasing the diameter of the lumen is going to increase your resistance, which is going to increase your blood pressure. It also increases water conservation by the kidneys. What that means is your kidneys are essentially going to take water from your future urine and they're going to put that water back into your blood. Now, what that will do is it will increase your blood volume. Increasing blood volume increases blood pressure. Renin, angiotensin, aldosterone RAA system function is also important with regulating blood pressure. The RAA system activates when there is a decrease in blood volume or blood flow to the kidneys. These changes indicate to the kidneys that there is low blood pressure. In response, your kidneys are going to produce and release into your blood a chemical called renin. Renin is going to change a chemical called angiotensinogen. Angiotensinogen is produced by the liver and placed into the blood. When renin changes angiotensinogen, it changes it into a chemical called angiotensin I. Angiotensin I is going to be acted on by an enzyme called angiotensin converting enzyme. Now, angiotensin converting enzyme is produced mostly by the lungs, but also by endothelial cells lining your blood vessels and kidney epithelial cells. So when angiotensin converting enzyme acts on angiotensin I, it changes it into a highly potent hormone called angiotensin II. Now, angiotensin II has many important functions. One, it stimulates an increase in cardiac output. Increasing cardiac output always increases your blood pressure. It causes widespread vasoconstriction, which increases peripheral resistance in your blood vessels, which also increases blood pressure. It stimulates the production of aldosterone by the adrenal glands as well. Now, aldosterone is a hormone and it has its own effects that are going to alter blood pressure. Aldosterone, when it's released by the adrenal gland, heads to the kidney. And at the kidney, it tells the kidney to increase sodium retention and increase potassium loss. So what that means is it tells the kidney, pull sodium out of the future urine and put the sodium back in your blood. It also tells the kidney to grab more potassium from your blood and put it into your urine so that you can excrete the potassium. Now, this effect actually increases water retention because water tends to follow sodium wherever it goes. So if aldosterone is telling the kidney retain more sodium, As the sodium moves from urine to blood, water will just follow the sodium along its osmotic gradient. Now, if you're pulling more water out of your urine and putting it into blood, your blood volume is going to increase, and that's going to increase your blood pressure. As I mentioned on the last slide, on the slide with our first hormone, angiotensin II will stimulate ADH release from your posterior lobe of the pituitary gland. Angiotensin II also will impact the brain, and what it's going to do there is it's going to stimulate the sense of thirst. And if you feel thirsty, what do? You're going to drink, and hopefully drink water. If you drink more water, you're going to absorb more water in the intestines. This is going to increase your blood volume and increase your blood pressure. Now, angiotensin II does have some other effects within the kidney itself. However, we're going to cover those in Chapter 23 when we do the urinary system. Believe it or not, erythropoietin, the EPO that you learned about in Chapter 18, also impacts blood pressure. Now, when you learned about EPO, you learned that it increases the number of red blood cells. Now think about what you've learned in this chapter. If you have more red blood cells total, wouldn't that increase your overall blood volume because you're adding more components to your blood? And if you increase blood volume, you'll increase blood pressure. Also, you learned in this chapter that red blood cells add viscosity to your blood. So the more red blood cells you have, the more viscous your blood becomes. So EPO is going to increase the viscosity of your blood. Increasing viscosity increases resistance to blood flow, which is going to increase your pressure. Norepinephrine and epinephrine, also released by the adrenal gland, specifically the adrenal medulla, after sympathetic stimulation. Now, epinephrine and norepinephrine, you learned for exam number 1, increase cardiac output by increasing heart rate and increasing contractility. By increasing contractility, you increase stroke volume, which will increase cardiac output. However, these two hormones do also alter blood flow in the body. They create vasoconstriction within the vessels of the skin and the abdominal organs, and vasodilation within your cardiac and skeletal muscle. Now, in order to understand these two effects and why they happen, you have to think about your sympathetic stimulation. Sympathetic is when you are in fight and flight. And what you want to do during sympathetic activities is to prioritize your blood flow to organs involved in fight and flight, which means decreasing flow to organs not involved in fight and flight. So if you think about these effects, the vasoconstriction reduces blood flow to the skin and abdominal organs, which are not involved in fight and flight, and vasodilation, which will increase blood flow to the cardiac and skeletal muscle tissue, which is more highly active during fight and flight situations. All right, so far, all the different hormones have led to an increase in blood pressure. So there has to be something to decrease blood pressure. And that's the hormone atrial natriuretic peptide, or ANP. ANP is made by the atria of the heart. So not only are the atria receiving chambers for blood, but they're also going to produce a hormone and act as an endocrine tissue. Now, the effects of ANP are all going to reduce your blood volume and your blood pressure. For example, they're going to increase sodium excretion by the kidney. So your kidneys are going to be told to pull sodium from your blood and to put it into your urine. Now, if you do this, water is going to want to follow the sodium. So if your kidneys are told, excrete more sodium, water is going to move from your blood and into your urine, increasing your urine volume, but at the same time, decreasing your blood volume. And if you decrease your blood volume, you decrease your blood pressure. A&P also reduces thirst, meaning you're going to feel less thirsty. You're not going to drink water because drinking water would actually make your problem worse. If you were drinking lots of water, you would be adding water to your blood, increasing your blood volume and increasing your pressure. A&P also will block the release of antidiuretic hormone, aldosterone, epinephrine, and norepinephrine. So it has the ability to block various hormones that all raise blood pressure. It also stimulates peripheral vasodilation. So that means arteries throughout the body are going to dilate. You're going to have a decrease in resistance, which is going to lead to a decrease in blood pressure. Now, let's turn our attention to capillary exchange. Capillary exchange is the two-way movement across your capillary walls. Now, recall from our last module that capillary hydrostatic pressure ranges from about 30 millimeters of mercury at the arterial end and declines as you move across the capillaries to about 10 millimeters of mercury at the venial end. Now, there are three different routes for crossing capillary walls. You can pass through the endothelial cell cytoplasm, meaning you have to be able to cross the plasma membranes and cross the cell. Intercellular clefts, those little gaps between the cells, and fenestrations, those pores passing through the cells if they're present in that particular capillary. The most important mechanism of exchange across the vessel wall is diffusion. Now remember, in diffusion, chemicals are moving from areas of high concentration to areas of low concentration, meaning they're moving down their concentration gradients. This movement does not require ATP, so it's very user-friendly for the body. Now, diffusion is only possible if your solute can pass across the plasma membrane, or it can find passages big enough to pass through, meaning it can find a fenestration, an intercellular cleft, an ion channel, or use a carrier protein. So as long as you can find a way across, your solute can move by diffusion. Transcytosis is also used to move material across capillary walls. Recall from A&P1 that transcytosis requires the use of both endocytosis and exocytosis. So the endothelial cell would use endocytosis to bring the chemical into the endothelial cell, and then it would use exocytosis to release the chemical on the other side. Now, transcytosis only moves a very small fraction of your solutes. It can be used to move fatty acids, albumins, some hormones like insulin, but only a very small amount of material is moved by transcytosis. You also can use filtration and reabsorption to move materials across your capillary wall. In filtration, you are removing a fluid and the substances within it from your blood. Now, filtration is going to involve hydrostatic pressure to force fluid across that selectively permeable membrane. Now, the hydrostatic pressure we're using is the pressure of blood within the vessel. So we're going to use blood pressure to push water and the solutes within it from the blood across the capillary wall and into your tissue. Reabsorption is going to return fluid and solutes within it to the blood. So think the re in reabsorption means you are going to return your fluid to your blood. Reabsorption is going to be governed by osmotic pressure. Now, both of these mechanisms are very important when considering capillary fluid exchange. Typically, across a capillary bed, filtration occurs at the arterial end and reabsorption is occurring at the venal end. Now let's talk about your hydrostatic pressures because those are going to help you filter. Hydrostatic pressure, again, is the physical force exerted by a liquid against a surface, in this case, your capillary wall. There are two hydrostatic pressures at play across your capillary wall. The first is capillary hydrostatic pressure, which has a pressure gradient of 30 millimeters of mercury at your arterial end to about 10 millimeters of mercury at your venal end. Now, the goal of capillary hydrostatic pressure is to push fluid from your blood outward across the capillary wall and into interstitial fluid. You also have what is called interstitial fluid hydrostatic pressure, and this is a pressure that's actually being created in the interstitial fluid. Now, the pressure in the interstitial fluid is about -3 millimeters of mercury. This negative pressure actually creates a little bit of suction, which helps to pull water and solutes from your blood outward across the wall and into interstitial fluid. So both of these pressures in their own way help to promote filtration. Now, using them, you can calculate what is called net hydrostatic pressure, which is the total filtration pressure you have across the wall. To calculate net hydrostatic pressure, you take your capillary hydrostatic pressure and you are going to add to it your interstitial fluid hydrostatic pressure. Now you're going to add the interstitial fluid hydrostatic pressure as a positive value because it is adding to filtration. So at the arterial end, your net hydrostatic pressure would be 30 plus 3 for a total of 33 millimeters of mercury. At the venal end, capillary hydrostatic pressure is 10. So your net hydrostatic pressure would be 10 plus 3 for a total net hydrostatic pressure of 13 millimeters of mercury. Okay, now let's talk about colloid osmotic pressure because this is the pressure that promotes reabsorption. Colloid osmotic pressure is created by the proteins, the solutes, within your solution because these proteins draw water to themselves. So they want to bring water to them. Now, there is blood colloid osmotic pressure, and this pressure is created by the plasma proteins located in the blood that can never leave the blood. Now, blood colloid osmotic pressure in a healthy person is approximately 28 millimeters of mercury. So you've got this really strong BCOP that is pulling water out of your tissue, across your capillary wall, and into your blood. Now you do have proteins in your interstitial fluid as well. So there is some colloid osmotic pressure in your tissues, and this is referred to as tissue colloid osmotic pressure. In a healthy person, this is approximately 8 millimeters of mercury. So this pressure is trying to pull water from your blood across the wall and into tissue. So tissue colloid osmotic pressure is actually trying to filter you. So you've got two colloid osmotic pressures. Each is trying to pull water in a different direction. Now, using these pressures, you can calculate what is called onconic pressure, which is your total pressure for reabsorption. To calculate onconic pressure, you take your blood colloid osmotic pressure, which is 28 millimeters of mercury, healthy person, and subtract from it your tissue colloid osmotic pressure, which is 8 millimeters of mercury. So if you have 28 minus 8, your onconic pressure, your reabsorption pressure, is 20 millimeters of mercury. Now, using this information, you can actually figure out what's happening across your capillary wall at any point in time. You can take your filtration pressure, the net hydrostatic pressure, and subtract from it the onconic pressure, which is your reabsorption pressure. Now, if you are filtering, you will end up, after doing this math, with a net filtration pressure, and this net filtration pressure will be a positive value. If you subtract net onconic from net hydrostatic and you have a positive result, it means your net hydrostatic pressure, your filtration pressure, was the higher value. However, if you do this math and get a negative value, a negative value is telling you that your onconic pressure was the highest value, meaning reabsorption is stronger. So a negative result is giving you what is referred to as your net reabsorption pressure. So let's do an example. So think about the arterial end of your capillary. Your net hydrostatic pressure was 33 millimeters of mercury. Your onconic pressure was a nice 20 millimeters of mercury. If you subtract these values, you end up with a positive 13 millimeters of mercury, meaning at the arterial end, you have filtration occurring. However, blood flows along the capillary bed, and at the venial end, your net hydrostatic pressure is a lot lower because your capillary hydrostatic pressure, that big push out, has actually decreased over time. So now your net hydrostatic pressure is only 13 millimeters of mercury, but your onconic pressure has not changed. That is still that 20 millimeters of mercury. So if you do the math problem now, you have 13 minus 20 for a value of minus 7 millimeters of mercury, indicating reabsorption happens at the venial end of the capillary. Now, that means that with this balance of pressure, there is going to be a point at some place along that capillary where reabsorption and filtration are equal. And at that point where you have this zero value, nothing actually happens. No filtration and no reabsorption. Now, daily, you actually filter approximately 24 liters of fluid out of your capillaries and into your tissue. Your average blood volume, not considering gender, is about 5 liters. So that's pretty impressive that you can actually filter so much out. The reason you can is that as you're filtering the fluid out, you are reabsorbing it at the same time. So across the capillary wall itself, you can reabsorb 85% of what you filter. However, that does mean filtration and reabsorption are not equal, and that you're leaving behind about 15% of what you filter in your tissue. Now that would create a harmful situation because it's going to lead to tissue edema, Your tissues could start to swell, and blood volume is going to plummet. However, that's why you have your lymphoid system. Your lymphoid system has the ability to actually collect the other 15% and return that volume to your blood. So by adding in the function of the lymphoid system, what you filter is guaranteed to be returned to the blood. Now, this lymphatic removal is going to have some big benefits. It's going to ensure that you've got good communication and exchange between your plasma and your interstitial fluid. It's going to help accelerate the distribution of chemicals such as your nutrients, hormones, and gases. It's going to assist in the transport of insoluble lipids and proteins that can't otherwise enter the blood across capillary walls, but they can cross a lymphatic capillaries wall, and by flowing through the lymphoid system can eventually be deposited within the blood. This exchange also produces a flushing action, so it has the ability to flush fluid out of your tissues and things accumulating within them, such as bacterial toxins and other chemicals. By flushing these things out of your tissue, you carry them to other lymphoid structures, which can lead to the initiation of immune defenses if needed. Now, filtration and reabsorption, and then the lymphoid removal, usually functions normally. However, it's not a perfect system and sometimes things go wrong, and you get things like edema. Edema is a swelling of your body tissue because of an accumulation of excess fluid volume. Now, you're usually not aware of the edema until your tissues have swollen over 30% of normal. And that's because once you get over 30% of normal, nociceptors, your pain receptors, become triggered, making you aware that something is wrong. Now, the reason you get edema is that for some reason, filtration is exceeding your reabsorption. So please pardon the typo on the slide, it should be reabsorption. Now, there are various causes for edema. So as a clinician, edema is your symptom, but you need to run a checklist to try to figure out what actually caused it. So, for example, you could have increased capillary filtration. So for some reason, your net hydrostatic pressure, that force causing you to filter, is higher than normal, but you are reabsorbing at a regular rate. This would start to leave more fluid out in your tissues, causing them to swell. This happens in individuals suffering from kidney failure. When your kidneys start to fail, you're not able to move excess water volume from your blood and into urine, so that excess water volume stays in your blood. This excess water volume is going to increase your overall blood volume, which increases your blood pressure. So that means your arterial blood pressure goes up and your capillary hydrostatic pressure goes up. If your capillary hydrostatic pressure increases, your overall net hydrostatic pressure increases as well. This also happens if there's poor venous return. If you have poor venous return, you are leaving a greater volume of blood in the systemic circuit. So you have increased blood volume in your arteries, increased blood volume in your capillaries, in your veins, and this increase in blood volume is going to lead to an increase in pressure everywhere, including the capillaries. And if you increase pressure within the capillaries, you increase that net hydrostatic pressure, and you start to filter more. Now, if filtration is fine, perhaps you are having an issue with your capillary reabsorption, so your onconic pressure is not normal. So you're filtering the same, but you are reabsorbing less. This could be caused by, let's say, liver failure. In liver failure, you don't produce plasma proteins. Your liver is failing to function, so it is failing to make the plasma proteins. That means in your blood, the concentration of your plasma proteins plummets dramatically. If you have a lower amount of plasma proteins, your blood colloid osmotic pressure is no longer going to be 28 millimeters of mercury. It's going to decrease drastically too. And remember, BCOP is your only reabsorption pressure. If it declines, you reduce your ability to reabsorb across the capillary wall. You could have an increase in capillary permeability. So maybe there's been some kind of damage to the capillary wall and it's just leakier than normal. This occurs after trauma, where the blood vessels themselves might have small tears due to a strain. These areas of damage allow plasma proteins to leak from your blood and into tissue. Now, what that's going to do is it's going to add more protein to your interstitial fluid, which is going to increase your tissue colloid osmotic pressure. And remember, tissue colloid osmotic pressure promotes filtration. So that's going to start to pull more water out of your blood and into tissue. Or you could just have obstructed lymphatic drainage. Remember, your lymphoid system is responsible for collecting the 15% of your filtered fluid that got left behind because it could not be reabsorbed across your capillary wall. So what if this fluid flow is blocked? Well, what that means is that the 15% that you can't reabsorb actually stays and accumulates inside your tissue. So that could lead to some severe effects as well, but we'll be talking about those in our next chapter.